Hello, and welcome to the third webinar in the TOSCA Implementer Series. Today, we will learn about using TOSCA in industrial manufacturing. Just a couple quick notes before we get started. Our webinar today is being recorded and live streamed. We are going to hold the questions until the end, but please feel free to add them in the question and answer box anytime during the webinar. Again, time permitting, we will get to them. If we do not get to them during the webinar, we will follow up after the webinar. We have two speakers today, both co-founders of CPLANE, and we are very excited to have them with us today, John Casey and Brandon Williams. A little bit about CPLANE. Brandon, can you advance the slide?
I can. Sorry,
awesome.
Deeper into our presentation here. Here you go.
There we go. So just quickly, so that we know that these guys are legitimate. This is CPLANE is a Silicon Valley software company. They are the orchestrator of orchestrators. They have many roots in telecom and cloud, and we're going to learn a little bit about their use case today. We are going to round out our webinar with Chris Lauer, who is the chair of the TOSCA Technical Committee. He's also the CEO of Ubicity Corporation. So we are really excited, and I think that you folks will find, I am confident that you will find this webinar eye-opening. And with that, so Brandon, we're going to start with you. Take it away.
Great. Thanks everyone for joining. We're going to cover a wide range of ground today because we're really talking about the convergence of modern IT architectures, including a lot of cloud technologies like TOSCA, with the physical world of industrial manufacturing, right, which is often referred to as OT, or operational technologies. And this is one of the main events that's happening with digital transformation in industrial manufacturing, Industry 4.0, and particularly where John and I are involved in the Open Process Automation Forum. And we'll try to introduce a little bit of context for this pilot that we're going to be giving you a live demo of today. And this demo was, or this pilot system, this project that we did, was in working with ExxonMobil. They're really the leaders in this transformation of industrial automation for the process industry. And they collaborated with us to try to see if we could bring industrial systems and cloud architecture technologies together. So that's what you'll learn about here. As Dee mentioned, I'm co-founder with John. My background is in telecom and infrastructure software, and was once a nuclear submarine officer for the Navy, so which is a strange kind of anchoring in the industrial world. John, do you want to give your introduction just for a moment?
Sure. John Casey, CTO and co-founder of CPLANE with Brandon. My background is in about 30 years of distributed computing in the areas of security and surveillance, telecom, and cloud and orchestration.
So you can imagine who does all the work in our company. Pretty clear. So we're going to start off at some very high levels. So for everyone who is a regular member of the TOSCA subcommittee, this will not be, you will object to some of the things that, the simplicity with which I present things. But we're also drawing an industrial crowd and introducing some concepts to the industrial manufacturers. By the same token, I'm going to talk about industrial control systems, which will not satisfy anybody on the OT side. So everybody will be unhappy with this, but I think we'll have a common understanding at the end. First is, what is orchestration? When you think of orchestration, there's a lot of use of the term of orchestration. I really want to think about, automating complex tasks, coordinating between lots of different technologies, layers, systems, locations, etc. But then also about the lifecycle management. How do you start an application, upgrade an application, deprecate an application? Same thing for a service or a piece of equipment. That's really what we're talking about with orchestration in this context. So let me give you a very short history of orchestration. Orchestration is not new at all. The only thing that is new is the complexity of the systems. And so the idea of orchestration goes back to IBM and maybe even before Tivoli, in a workload scheduler in mainframes. You had one large piece of equipment and you were trying to share access to all the resources in that box or tower, with competing workloads. And so a lot of what we use in orchestration today really was pioneered in that environment. Another example of orchestration that you might be familiar with in the 90s, if you were part of a big corporation, you were told, leave your computer on over the weekend because the IT department was orchestrating upgrades, security patches, application updates, whatever it was. And so orchestration certainly is prevalent, in that arena. As the telecom industry deregulated and telecom services really took off, the telecom industry started building some very sophisticated network management tools. And of course, Cisco has their set of network management orchestration tools. I think they probably have 8 or 10 at least. Juniper has theirs, Arista, et cetera. So the telecom industry is a very large user and creator of orchestration technologies. Now, as we started getting into the internet, we're going to call it middleware if it's WebSphere or BEA, but there just needed to be this automation, coordination, lifecycle management in the three-tier architecture of the internet. And then as the internet grew into the Web 2.0, as it's known, you think of the web scale companies as well as the cloud companies, right? So not just Amazon, but Amazon's back end that they're now selling as AWS. You really get it into infrastructure as a service. And technologies like Kubernetes and OpenStack and lots of other orchestration tools, come out of that development. Now we're getting into the era of edge, and the edge has a lot of the technologies of networking and Web 2.0 and using Kubernetes, et cetera. But it has this added complexity of both being distributed and in many cases hyper distributed, and also that it interacts with the physical world. And that's really where our story today is about, is how is all of this legacy of technology of orchestration coming into the physical world or the OT systems. For those that don't know, what is TOSCA? First of all, TOSCA is a standard. That's part of the OASIS group who's hosting this webinar today. The second is that TOSCA is really used to manage applications in the cloud, and that's where it came from. As well as some network services for telecoms. That's how it's being used. And more specifically, what is TOSCA? TOSCA is really just a very structured language or description that describes applications, the infrastructure that those applications need to run on, as well as any dependencies. And you're actually going to see that in our demonstration, as we use TOSCA to orchestrate and converged IT/OT system. Again, who are John and I, who is CPLANE, coming out of Silicon Valley with a lot of depth in telecom and cloud. We have honed our expertise in orchestration by creating SDN solutions for IaaS. Really started in WAN orchestration, and then have moved into distributed systems or distributed cloud orchestration. And really this concept of an orchestrator of orchestrators. You probably know that Kubernetes is an orchestrator. OpenStack is an orchestrator. Cisco's NSO, Network Service Orchestration, surprisingly, is an orchestrator. So with system orchestration, you're really oftentimes managing multiple orchestrators to produce a single system. And you're actually going to see that today. So now let's talk about the other half of the equation in our pilot project with ExxonMobil is what is an industrial control system? And this is a grossly simplified diagram, but let's start at the bottom is where these systems connect to the physical world. And that is in sensors and actuators. If you think about turning on a burner, turning down a burner, opening a valve, turning a pump on, reading a temperature or a pressure or differential pressure, or any of the things that go into a physical manufacturing system have to be sensed, and that data has to come up to some kind of intelligence. And that intelligence is occupied in another tier of the architecture where the control applications run. And these control applications are very different than cloud applications. But a good way of understanding this stack is maybe think about a self-driving car, right? And you have the LiDAR that's out sensing the physical world, and that is being fed into some kind of control application that's making decisions and other decisions about maybe moving the wheels, or accelerating or decelerating, or applying the brakes or whatever it is supposed to do. It has that loop into the physical world. And so you can see the sensors and actuators, in a loop. And then above that is, a fairly, I would just say, a modern sort of stack of IT infrastructure, compute that's running a data historian, that is maybe having some advanced controls of the whole system. And this is a fairly, certainly grossly simplified, but fairly accurate portrayal of what an industrial control system is. The reason this is important, and as we'll explain in the next couple of slides, is that this stack of digital technologies, principally, there are some analog technologies in here, but this stack of technology is called a distributed control system. And today, the entire stack is developed by one vendor. Each vendor has its own proprietary DCS, or distributed control system. These are names like Honeywell, Emerson, Siemens, ABB, Schneider Electric, et cetera. Those are the giants in the OT world that build these proprietary stacks of technology. If anybody's having a flashback to mainframes, it's probably a good comparison. Going back to the IT industry, as late as the early to mid 80s. Another important thing about OT, or industrial control systems, or OT systems, is that they have people in the loop. These are operators. They have people in the control room. This is a different thing than running a data center, right? If your Facebook app slows down or crashes, it's not the end of the day. If you're producing oil and things are running at high temperature or high pressure, there's environmental concerns, there's safety concerns. It's a very, very different environment. And so the reliability and deterministic nature of these DCS systems actually has served the OT industry very well. However, for a lot of reasons that I'll mention in just a moment, the large industrial manufacturers are moving the industry through an open standard called OPAF to an open architecture. So all of this proprietary stack gets blown up and gets put into a open architecture where you can have multiple vendors sensors. You can have multiple vendors software running on different hardware in the control applications. You can connect out to the cloud. You can integrate ITOT or industrial IoT systems, into the control architecture. And it's very exciting, just a step function change in functionality for industrial manufacturing. This is happening worldwide. However, if you're in the IT industry, I want to point out some very important similarities between the old system and the new system. You still have the same operators. These people are expert in running that physical plant, and they're not going anywhere. They're necessary. And so you have to make this very modern system of really almost entirely IT technologies, not entirely, but you have to make it so that it's still operable by the same people. And in many of these cases, if you're on an offshore drilling rig, the nearest DevOps engineer might be 1,000 miles away. And that might sound like paradise for some of you. But if you are trying to fix these systems, then that could be a problem. So you really have to have a very reliable system in a modern IT stack. And that's really what this demo and pilot is about today. I mentioned the reasons for making this transition. Just briefly, there's a lot of security concerns about how easy it is to keep the security defense around these proprietary systems. You're hearing about that in the news a lot. There's a lot of big data analytics. The total cost of ownership of a proprietary system, of course, is very high. And then the ability to make upgrades to the system. This DCS system will stay in place often for as long as 30 years, basically without being touched. I know some of you in the banking industry can relate to your 30-year-old mainframes running in the basement, but in the IT industry, that's not normal. This is a very significant change. So, in working with ExxonMobil in this pilot, the goal was to see what is the art of the possible, and we chose a very narrow slice of the life cycle of an industrial control plant to show that, and that was the startup phase. And the idea was, could we demonstrate a startup of a control system, which would normally take about 50 to 100 engineering hours to accomplish? Could we accomplish that maybe in 10 minutes, right? So 100 hours to 10 minutes, that's a pretty big savings using a lot of automation. But could you do it without IT expertise? And in the pilot that John's going to run, it's going to be literally 3 buttons that are going to initiate orchestration actions to perform this task of preparing an industrial control system to run. And that's what we're going to show you today. And one of the important tools for that is TOSCA. And if you're new to TOSCA, then we'll maybe just give you the slightest bit of insight into what TOSCA is. If you're part of OASIS and the TOSCA community, then you already know what it is, and you should be very interested in that it's getting applied into very, very different environments than cloud application lifecycle management or NFV or SDN type applications. Okay. So let me just try to set up the demo for John. Because this was done in 2020 and during COVID, we actually built this system in 3 different locations, not three versions in 3 locations, 1 version, 3 locations. So this advanced compute portion is actually hosted in San Francisco. Our software, the orchestration software, is in a data center in San Mateo, California. And then a lot of the controller parts of of this pilot are actually in New York. So distributed across the country is a control system for what we're simulating is a single chemical process. In our demo, all of the I/O is simulated. We didn't actually build a chemical plant to do this. We're running this in a simulation, but all of this infrastructure is what we're managing, as well as the software that's going to get deployed on it. So just talking briefly, when we're introducing orchestration, and John really has been the pioneer of introducing orchestration into this industrial control environment, the way that we describe it in terms of IT/OT integration is that you starting with the physical system. You have to know what the digital infrastructure is, right? What's the capacity? What's the capability? What's the description of the of the infrastructure? And that gets ingested through a DMTF redfish. Some of you are familiar with that, into our orchestrator. The next thing you need to know is kind of what are all the requirements. I talked about application lifecycle, what the infrastructure is, and what the dependencies are, and all of that gets pulled into through using TOSCA, describing how this environment's going to work into our orchestrator. And something that's very unique is, how do you actually then match this digital infrastructure with the actual manufacturing process components themselves. And what I mean by that is those control applications that I talked about, the control loop, knowledge about the sensors and actuators, just an understanding of that OT side of the house. We actually work closely with a very large OT vendor called Schneider Electric, and using their environment that's called a 1499 design tool, we worked with them to integrate into their, I'm going to call it an application engineering environment. That's not going to satisfy anyone, but this is really the heart of the OT system. We were able to interface with that and pull that into the orchestrator. From there, we're able to perform the task that John's going to show. This is another look at kind of the same thing. When we're trying to explain orchestration to the OT industry, we walk them through, what an orchestrator does, right? And I think of TOSCA as being like the programming language of orchestration. And so what an orchestrator does, it's going to ingest the physical system, knowledge, right? The topology, all of the understanding of the physical digital infrastructure. It's going to understand all of the rules, the structure, all of the knowledge for how that system should run, and that's going to come in through TOSCA. And then we're going to have some pretty standard ways to communicate with the infrastructure and other systems that are involved in this whole process. And in the CPLANE orchestrator, we're going to be building a digital twin model in our information model, and we're going to be running through the steps of an orchestrator, right? That orchestration is essentially moving from one state to another state. And this is not New York to Florida. This is, from not running to running, if you're an application. So analyzing the state, knowing the rules and how that application gets deployed, for example, and then being able to create all of the steps that are necessary to make that happen through the workflow engine, and then to schedule those and make sure that they occur. And being able to do that in multiple domains of infrastructure is critical. One of the things we talked about orchestration is that it has to coordinate. So coordinating among the, between the network, the computer layer, the virtualization layer, any security requirements, as well as the OT, process control technologies. You have to coordinate all of this dynamically in order to make this work successfully. And the last thing I'll mention here before we turn it over to John is that you really want to get into, it's 3 buttons, as I mentioned. The first one is when we're discovering the underlying infrastructure. We show the points of integration with the OT side or with the Schneider Electric. The second over here is load system definitions, and that's when we, ingest the TOSCA document and sort of program the orchestrator. And then the third is when we, kick everything off or run the orchestrator and actually do the installation. So what you're going to see, and as I turn it over to John, is basically 3 mouse clicks that, quite honestly, even I could do if you want to talk about little or no IT skills. And you could deploy an entire control system on distributed architecture.
Brandon,
John,
before we get
I'll turn it over to you.
Yeah, before we get into that, can you go back to the topology? I want to make a couple of points here.
Yeah, please.
So, guys, for you familiar with TOSCA and cloud and OpenStack and its origins and deploying cloud, resources in the cloud, as we all know, right? You have an unlimited or almost unlimited resources, and they're all pretty much the same. I mean, they may vary by, GPU this or, number of memory, memory or, whether it's East Coast or West Coast. But for the most part, you're deploying across a common set of infrastructure. And in some ways that makes, orchestration quite easy. And I want to point out in this picture that in an edge environment, specifically an industrial edge environment, that that's not the case, right? If you look at this diagram here, these little boxes, the orange boxes and the black boxes represents what Brandon was talking about was this control structure, right? So the compute devices that are running a specific task to measure a piece of data, like a temperature or a pressure sensor, and then turning around and actually making some calculations and opening a valve and closing a valve. And so these kind of boxes around, let's say these, boxes around these three sensors or the two sensors, there's some commonality amongst groups of devices, but in general, you can't look at a plant as a common set of resources deploy devices anywhere. And when we get into why we're using TOSCA and how we're using TOSCA, this is a really important point, is that we really need to land the control block application in an appropriate place that's next to a sensor or an actuator. And that's really one of the main differences if you're coming from the TOSCA world, how this is very different. And we jumped through a lot of hoops, and we're working with the OASIS group in their 2.0 specifications to provide some domain-specific knowledge to make this easier and to kind of drive this TOSCA standard forward, but also move it into the industrial arena. Okay, thanks, Brandon. So with that said, let's go build a manufacturing plant. Let me share my screen, and I'm going to walk you through. If any of you guys have ever seen in Hollywood a manufacturing plant, maybe China Syndrome or Chernobyl, right? There's guys standing around in a control room. They're looking at these big screens. Typically, these screens are what's called HMIs. And this is it's a human machine interface. Essentially, it's describing what's going on in the manufacturing plant. And what I'm showing you here is basically a blank HMI, right? All these question marks, meaning that there's nothing deployed, there's no data coming to the system. And once we're done deploying the applications, we'll come back to the screen. We'll actually show that the system is deployed. You'll see some numbers here. We'll actually, this is actually an HMI to run a chemical process. So we'll actually go and run that chemical process. Why don't I just bring up, I'm going to tell our orchestrator in this window so you can see things happening. This is our, essentially our front end to our orchestrator for this pilot. And as Brandon talked about, there's really sort of three steps that we're gonna go through. One is we're gonna do discover on this control infrastructure landscape, and we're going to build a topology and understanding of the devices in the plant. And then we're going to pull in other information so we sort of give life and understanding to that topology, understand where the sensors and actuators are, and we'll have a really good rich topology that we can work off of. And then this middle button here will actually load a TOSCA document and deploy a TOSCA document. And then this last button here is that we can actually see what's running on the different devices and look deep inside that. And again, we've developed this system so that you don't need DevOps engineers. Your existing chemical engineers or process control engineers can work with this system inside a plant. So I'm just going to double click on here. And what we're going to do is you'll see the tail of our orchestrator here kind of scroll through. I'm going to go ahead and hit discover. And what this discovery is going to do, we're using as part of the OPAF standard, which is a standards body of standards, right? So standard of standards. We're using a technology called Redfish, which is an on-device agent on each of these PLCs, these DCNs, the compute devices that you saw in that picture. And what it allows us to do is it allows us to inquire about the makeup, the capabilities, the characteristics of each of those devices, maybe what I/O is connected to, what bus architecture is connected to, and we can pull that into a topology to make good inferences and decisions about that plant, right? And so I'll go ahead and just refresh the screen here. And it takes about, I don't know, about 90 seconds, I think, to pull all this information in from, we have 14 PLC devices. So we'll pull that in, and then we'll double click and we'll show you some of the information that we're gathering. This is very analogous to if you were to go to deploy an Amazon Web Services, you might have a sidecar file that describes, your account information and maybe what you have available, to you within, with Amazon. Well, in the industrial control system, you don't have that. And so what we need to do is we need to build up this definitional topology, this information model, if you will, about the industrial plant. I'll go ahead and hit refresh again, and we're starting to see some additional information come in. And when this is done, I'll pull you through some of this stuff. While I'm talking about that, I do want to mention what we're doing in OPAP is that we are defining a standards of standards on how, just like ETSI NFV defined what a network, orchestration standards-based could be around telecom networks. What we're defining is basically how you break down those layers to provide interoperability, portability, security of an industrial control system. That standard is made up of different groups. There's a security group, there's a application portability group. I actually run the orchestration, I co-chair of the orchestration subcommittee within that, within the standard. And we're driving the definition of TOSCA and Redfish and OPC-UA, essentially all those data models into the standard, so that an orchestrator has complete understanding of a control system. So I'm going to go ahead and hit refresh one more time. And now this has all been filled out. And so now this is just, this basically, you've got the name of the actual device, maybe you have its IP address, you have its bus architecture. This bus architecture, or the name of the bus, describes what I/O, what actuators and sensors, the bounds of which it can control. I'm going to go ahead and double click on EC104 here for a second. And as you can see, there's a lot more detail about this device that we're getting. And this is all coming from Redfish. It's basically the bounds at which it can run, the temperature at which it can run, whether it can be in an explosion area. And so all of these things about this device are taken into consideration when we're thinking about, or when we're calculating from a TOSCA and an orchestrator perspective, where to place control blocks. And so you can sort of see there's sensor information about what this device is connected to. This is all coming from Redfish, right? There's also the classic information you would want about capacity of the device, how much memory is available. There's probably something around CPU here as well. So memory, CPU. And so as I look at this device, now I understand its capacity. I understand what I/Os it's connected to. I understand, how much compute headroom it has. And as we start laying applications on here, we know then, well, how much processing that device can handle and what that's connected to. Okay. So now that we have this topology and it's built in a database that you can make good decisions on, you can make decisions about, one of the things that we're kind of defining in the OPAP's orchestration system is when you make choices about how you deploy applications. First, you want to place the application logic as close to the output sensor as possible. If you can't do that, the second piece is, well, let's place it as close to the input sensor as possible, right? And if that can't be satisfied, maybe you put it on the same network segment or within a couple of milliseconds away from either input or output. Maybe place it in between those two, right? And so that type of language needs to be codified into TOSCA, right? Or codified into our system in some way to be able to make those decisions. Before I jump on to the TOSCA piece, this is the definitions of the devices, of the compute devices that we talked about and the makeup of those devices. If I click over here to assets, another thing that we've actually pulled into the system in a separate way, what are those actuators and sensors? What's the equipment that we're trying to deploy on, which is a water chiller, a product charger, a cooling control system, an agitator, which is basically a big mixer, right? Is that all of these pieces of equipment have actuators and sensors, and what we're doing is we're placing the control logic as close to those equipment as possible. So we're talking about a really constrained environment. So I'm going to go ahead and what we're doing is basically tying these two together. The compute modules. Now we have addressability and understanding of what the equipment they're actually connected to. I'm going to jump back here, and now I'm going to go from discovery. We're going to go to deployment phase. So what we're going to do is, and I'll walk through the TOSCA in a minute, what we're going to do is we're going to take this little TOSCA document, and we're going to drag it on our product, and we're going to consume this TOSCA document. I'm going to go ahead and bring up and talk about the TOSCA document for a second, because this is a TOSCA presentation. We used, first of all, let's talk about where we are in the phases of using TOSCA. We're using TOSCA 1.2 or 3 in this demonstration. We're over the course of the next year, we're going to be working with the OASIS Foundation and defining our own domain-specific attributes of TOSCA for the industrial control system. We were somewhat limited in what we could do with the TOSCA 2.0 stuff. It was sort of deep-rooted in its legacy. So we made some choices, some architectural choices to get this done. But we have a lot of thinking and working to do to actually marry these things together. But anyway, we'll walk through it. So what we have here in a TOSCA document is a list of the applications. So we've got OPCU LDS, we've got Docker runtime, we've got Next Control runtime, which is supported on top of Docker, right? So there's a dependency there. We've got OPUA server, OPCUA clients. And then here we have things like the definitions of the infrastructure. We've had to define using attributes what that infrastructure is. So we've kind of grouped it by, what kind of device, Intel or ARM device, what kind of IO is it connected to? Is there an IO bus? And so we used the node abstractions to describe the redfish topology, or the information we got out of redfish. And then we used some policy groups to basically help us do that matching between the attributes and the requirements of the application up here to tie into that the capabilities that we defined in those node configurations of the infrastructure. We're using, let me see if I can expand this whole thing so we can just unfold all, right? Okay. So some of these you'll see that we're using Ansible to actually do some of the on-device work. And so, some of the things we sort of described here is how can you describe, application-specific URLs, right? That an orchestrator can understand. And we're using essentially the workflow. We're sort of defining, deploy and start and stop and delete using some of the workflow capabilities of the applications, right? So you can sort of see register and delete. I'm going to jump off of here. I think that's probably deep enough for this demonstration, and we'll go right into after we've consumed this TOSCA document. This is what it looks like in our system. You sort of see the applications listed here that you saw in that TOSCA document. And if I double click on these, the second column you see here is its dependency. And as everyone knows, in a dependency graph, you have to actually do things in that order, right? So before we deploy this next control application, we actually have to go and ensure that Docker is actually installed on these devices if that's how we're going to do it. In an OPC so this is a containment dependency, right? So this application is contained within Docker, so that stack on the device has to be configured. This is more of a relationship where in order to place an OPC server on a system, that there has to be an OPC GDS or LDS that exists somewhere in the network because it's a dependency on configuring that device. So that's also consumed in this TOSCA document. So we show some of the parameters. I want to sort of note this section here. As we sort of click through, you'll see that the deployment location and status is none. That's because we haven't done that matching from application intent and kind of matching that to the infrastructure. We'll do that when we go ahead and hit deploy, which I'll do in a second. So when we do that, I think the deployments takes about 5 minutes or so, 5-6 minutes. So we'll go ahead and hit deploy here. As you can see, the orchestrator is now working in background. What it's doing is it's doing this matching from what we have in the definition of the TOSCA document into the knowledge of what we have about that existing topology that we discovered. So I want to talk a little bit about TOSCA for a second. As this goes, I mean, this is just going to go in deployment. It's doing things in parallel. It's doing things in order in parallel. And so as this goes on, this will last about 5 minutes. I want to talk about TOSCA itself and go back to some of the things that Brandon talked about, which is in a control, industrial control world, you have different different actors that are running the plant. You have an engineer who designs the plant. You have, different structural engineers and mechanical engineers who are part of that design process. You have operations engineers who run the plant, day to day, right? And where does TOSCA come into this, right? And so one of the things that we're working on in the OPAF, the open groups, the OPAF world is, okay, how would this TOSCA get generated, right? We don't have IT, we don't have a DevOps person that could sit there and hack YAML files together, right? Well, early on in the design phase of a manufacturing plant, or even when they're upgrading manufacturing plant, there's a set of blueprints. They're called P&ID diagrams, or pipe and instrument diagrams. Typically, there's products from AutoCAD, Autodesk, Intergraph. There's a number of industrial specific CAD systems out there that are backed by a database that describe, the piping and the instruments and the actuators. One of the things that we're looking at doing in the forum is to take the data directly from a P&ID drawing and transform that into utilize the exhaust of that data, the metadata coming out of that, to drive a number of different processes to deliver a software-defined plant. Part of that is location of sensors and actuators, right? Information about those sensors and actuators that we can then pull into potentially a TOSCA. We can generate, skeletons of part of the TOSCA documents. The other piece that Brandon talked about is the engineering design tool. Now without getting into too deep, I mean, you could speak hours upon these engineering design tools, but there's languages, metadata languages called automation ML, or AML for short, that is, an XML description of the project and the control loops and the understanding of, what applications get put together. And then there's also OPCU information that we're getting actually from the live sensors. By pulling all this together, we can start to either generate most of what's in the TOSCA document. Also, the manufacturers might provide some details around their applications and how those are deployed as part of TOSCA. But what we really like to see is this sort of flow through from initial design of a plant through the process of actually deploying a plant. Now, what you're seeing here is we're actually going through that sort of last step of actually deploying a plant. And you're seeing this take about 10 minutes. I'm going to go ahead and double click on this, and you can sort of see when I double clicked on LDS coming back to the application, you can now see that we've actually chosen a device called EC101, and we've deployed the OPCUA GDS LDS on that device. We'll go ahead and click on, let's see, the next control runtime. And it's actually selected based upon the control loops that were developed and where those control loops actually have to run. So EC104, for example, is running specific control loops for the actuators and sensors that are connected to that device. It looks like this is actually done. I'm going to go ahead and just double click on here and ensure that everything is active. The OPCUA clients are all active. So this is actually now deployed. Before I go back to the HMI and show you the chemical process, I would just want to click back here and show you the deployed services, right? So now what we're doing is we're looking deep inside those devices and actually showing you what software is running. And a lot of the tag information here, these are tags and understandings that the control operator understands. They go back to this P&ID drawing. And so what we're doing is we're correlating the applications that we've deployed to the actual OT side or components of the system. So I'll just go ahead and click on what's running on module 100, which is an IO module. And we can actually show that these are the actual application tags. These are the sensors and actuators, the tags for those, and that we basically have next control runtime, and that's associated essentially with a reactor water chiller type of function block, right? So we're drilling all the way down into the actual inside the application that's running on this device. So this sort of gives you the system-wide understanding, and then you can kind of drill into each device and understand what's running on those devices. I'm going to jump back here, and we only have a few minutes left. I'm going to come back to the control process and actually show you now that we've deployed the function blocks, we've deployed the control loops, OPCUA is running, it's generating traffic and sending it up into this HMI, and now you can see all the question marks are gone, and it's ready to actually do some work. So let's go ahead and start the process, and you can now see the chemical process actually being created, and it's filling a tank up with some liquid, and it's going to be heating and agitating that liquid, and that agitation will create some sort of chemical reaction. Anyway, the system is basically up and running and ready for action. I'm going to stop there, and then maybe we can talk about some Q&A. This is running. Dee, how are we running the Q&A? Are you going to read the?
Terrific. Yes, I've got questions coming fast and furious now. Okay, great. So just let me say right off the top, if we do not get to your question, we will follow up. And Jane, if we could do some screen captures, that would be fantastic. I'm going to try and take them as they come in. Anyway, okay, so let's get started. Your talk is truly eye-opening. Thank you. So the questions. A stepwise timeline is missing from this otherwise excellent narrative. For example, what are the dirty design homeworks needed to get to these 3 clicks that Brandon mentioned? Step 1, understand the physical layout. Step 2, create the TOSCA docs. What are the implications of this method for digital twins? How are the simulator vendors taking this? I think John mentioned something about Schneider Electric. There's a lot of, give us whatever feedback you can related to the paragraph that I just read. So.
Yeah, no, I would say in terms of digital twins, there's the digital twin of the physical plant. That's really important in industrial systems. You go in and you change a valve, or you're trying to direct an operator, to close that valve or to troubleshoot that system. That's not what we're talking about. There's a digital twin of the physical process itself, right? The actual chemistry and physics and thermodynamics that are taking place. That's not what we're talking about. There's actually a whole study about process orchestration. It's not related to this. This is really the digital orchestration, or a digital twin of the digital infrastructure of the control system itself, and just the control system. And that's the modernization that's happening. And so digital twin is another one that gets used a lot. There's a lot of ways to think about that, but by having an orchestrated control system, then you can start making changes to how the plant operates. You're not actually operating the plant. Our orchestrator's not touching, isn't deciding when valves are open and that kind of thing. It's deciding where the applications are that actually make those decisions. So it's a good question, because there's so many of these terms that are thrown around. We have to try to frame it into that context. Hopefully that touches on some of what the question was about.
Okay, great. Thank you so much. Let's move to this next one. Is there a way to automate commissioning after deployment? Is this something you're looking into?
You mean like commissioning of a whole industrial plant? I assume. What John walked through with a control system physically in place, but no software running, to it actually running, and then you're opening valves and turning on pumps. Operators would not do that, right? I mean, this is an industrial system, but just showing that 50 or 100-hour step-by-step process can be reduced to 10 minutes is really meant to show the power of orchestration throughout the entire life cycle of running that plant and maintaining and upgrading the control system through all of its life cycle. And that's not possible today, right? As I mentioned, you implement it once, it's there for 30 years, has caused a lot of difficulties for the manufacturers. So they want to be able to install it cheaper and quicker, not in 10 minutes, but cheaper and more quickly, and then be able to evolve the control system on a regular basis, right? Like you get a new algorithm, a better algorithm. You've done some data analytics in your data lake, and you want to implement some kind of new control loop, directly into the control system. That's not possible in proprietary systems today without shutting down the plant.
Hey, Brandon, I think that one of the questions was, there's a follow-up to that, was I think he's talking about IO commissioning. And so if I can answer that, or you can.
Yeah, no, go ahead.
Okay, I think yeah, we did, there are some steps that are skipped in this to bring this down to a 10-minute demo. In a manufacturing plant, there's lots of things that need to be automated. And one of those is actually commissioning the actual physical equipment, right? Laying the tags out onto the, if you have an actuator, you pull it off the shelf, you get it from a manufacturer, you put it in your system. it's not automatically programmed with the tag that that the control engineer created, and therefore the question is can we automate some of that as well? We're certainly looking at that in OPATH. There's looking at utilizing OPC-UA and some of the functions in the OPC-UA standard that the orchestrator can, as you know, can talk multiple languages. OPC-UA is one of them. So the ability to kind of load up your physical infrastructure and then automate the tag definitions on your equipment is certainly one of the things that we're looking at in the OPATH forum.
Okay, so again, we do have a lot of questions, which is fantastic, but I just want to make sure if we can get through some of these. We have someone who's raised their hand and they're waiting patiently, Jingyi Zhao. Jane, could you please unmute him or her? Jingyi, are you there? Gosh. Okay. Let me go ahead and move to the next question. How does it use TOSCA to make deployment generic? It looked like you didn't have to provide any inputs. Are they all hard coded or provided some other way?
There were inputs to this, and we did not show that in this demo. But yeah, there was the zip file that I actually dragged on top of that user interface actually incorporated a number of files. One was the TOSCA definition, the instance definition. One was the our specific TOSCA object definition, which is the kind of the base class. There was the input files to actually the TOSCA document, and some of the data was actually coming from in our TOSCA definition. Some was coming from inputs, and some was being actually resolved by the topology. And then there was a fourth one that had some additional information for our orchestrator. So yes, we did use the. It wasn't static. So I think that was the question.
Okay, great. We're going to try Jingyi again. You're unmuted. Would you like to ask your question? Maybe I'm not pronouncing your name correctly. Okay.
It's Jingyi Zhou.
Hey, Jingyi, how are you?
No, I'm sorry. That is the pronunciation of the name is Jingyi Zhou. Right. If you have a question, they can ask. Hopefully, could be an audio problem.
Okay. We'll just leave it open and feel free to pipe right in. Okay, here's another question. From the demo, it looks like the network topology is already in place to allow for all the communication. Is TOSCA also the way to describe the network provisioning? That might be a Chris question.
We can answer it too. I mean,
okay,
Chris, feel free to answer the generic one, and I'll follow up with this.
Oh, why don't you answer the specific one? And
okay. Yeah. In this simple demo, the network, we did not try to address the network side of this. But yes, TOSCA can define networks, and you can utilize the information in a TOSCA document to provision your networks. One of the things going on in the industrial control system is something called time-sensitive networking. And essentially it's the underlay for OPC-UA, and it guarantees that packets arrive at their destination exactly when you expect them to arrive, no earlier or no later. As part of the definition of TOSCA going forward, and we're still working on this in the OPATH forum. In fact, we're actually having a presentation about TSN in the next OPA forum, is basically what you need to do to define that sort of network infrastructure in a TOSCA document. And you're going to see lots of in a industrial control system, depending on how big it is, a big oil refinery, they may have hundreds of networks and different security zones. And so, what you're going to need to do in a TOSCA document in that case is not only consume and understand the IO devices and how to place that, but it's also the security locations and ensure, things aren't put in a blast area, deploy applications in their appropriate place. And network was going to be a very big part of that.
Okay, terrific. Chris, do you want to add anything here?
No, I think that's an excellent discussion. I think, John, what this leads to is that clearly from your experience, there is specific application domain knowledge that is currently not expressed in any TOSCA type system. So with TOSCA version 2.0, our goal is to provide the ability to create domain-specific types and package those as profiles and leave TOSCA itself as a language specification in support of a number of different application domains. And so what we would be interested in pursuing is exploring how to express things like the latency requirements or the guaranteed networking arrival time requirements. How do we express that using the TOSCA language, and what extensions may be necessary to support those types of features? So it's very exciting to see TOSCA being used for a, like you said, a non-legacy application domain. And we'll continue to work together to remove any legacy concepts from the language and move things forward in as much a general purpose fashion as we can. So very exciting.
Yeah, thanks, Chris.
Quite an excellent demo. Thanks.
It's great to work with the guys in the OASIS TOSCA organization. Chris, we know you from a long time, and you guys are very responsive. So thanks.
Oh, likewise, appreciate it. Thanks.
So Chris, we're after the hour, but I know that you have some closing comments. I also have a question for you specifically. Could you describe the upstream feedback to TOSCA and maybe with some other examples? Again, folks, if we didn't get to your question, we will follow up with an answer after the recording. So be patient.
Yeah.
And Chris,
and as I just said, I think that this type of work is exactly what we're trying to do with TOSCA version 2.0. We are try to remove any legacy application constructs from the language and making TOSCA as general purpose as possible for orchestration, lifecycle management, and so on. And we're working closely with companies like CPLANE and with the OPAF more broadly to investigate those types of challenges. So this is excellent work, and we'll continue to keep the community informed as we make progress. On that note, we will continue to have these webinars every last Wednesday of every month. The next one is scheduled for April 28th, and during that presentation, Comcast will present how TOSCA is being used in the context of their business services. As many of you know, Comcast is the largest, or maybe one of the largest cable providers in the US. Most of you will know them as your internet provider, but they also provide business services to large organizations for network connectivity and what have you, and they're using TOSCA to manage those business services. So we're looking forward to a deeper dive as to how TOSCA is being used for delivering those services, and that's on April 28th. So we look forward to seeing everyone again there. So Dee and Jane, I think that's all I wanted to say.
That was great. That
Thanks,
was great.
guys.
I certainly learned a lot. Thank you guys so much. That was very powerful. Okay, folks, we'll see you on the next end user event that we have coming up soon. Thanks so much. That was great.